Right away. Um, Last week we saw how to check for normality. We saw the Shapiro-Wilk test and we saw the histogram. And we were able to analyze the histogram to draw conclusions whether it is fairly normal, like fairly bear-shaped or not, which is one of the prerequisites for us to do a parametric test, like the t-test, the ANOVA, and the like. So in some cases, when your data is really, really skewed and you cannot perform parametric tests, what you do is that you try to transform the data. Like you can do the log form of it. So, for example, we did weight last time, right? Let's just look at it again. This is the data set. We did we did go to analyze, which is a scale variable, a continuous variable to the dependent list. You can click on statistics and check outliers if you want to see outliers. That's overly very high values or very low values. In this case, if we have some birth weights that are really, really uh, high, like the babies were really, really big, those could skew our mean. So it's good to check outliers. Then for the plots, we will not want to see this one. We want to see histogram because we want to use histogram to check normality. Then you take this other one, normality plots with test. And then you take continue and you take OK. So when you do that, you have results. So if I share the result screen, so the first thing you look at it is you can scroll right down to your box plot to check your outliers. These are box plots. And like I explained last week, this line in the middle here is the median. And so if you want to look at it, you can try to draw a line to touch the y-axis. You see that it will be around maybe 33 or 3.3 kg or 33, 3,300 grams, which you can confirm by coming right up here to check. If you come right up here, you can look at the median, which I think we should be able to see it here. Yeah, 3,300 grams. So that was what the middle line in your box plot tells you. What we can call the 75th percentile. I think this is not the maximum value, rather. This is 75th percentile, rather. This is 75th percentile, this line up here, and this is the 25th percentile down here. All right. So we have the median, the 25th percentile, and we have the 75th percentile up here. All right. And then this is now the spread. In this, if you were to look at it in terms of mean, this would be a standard deviation, right? How spread the values are away from the median, up and down. And then these data points here show that there are some outliers. And these outliers, it doesn't mean that 147 is a value, but it's a placeholder. So you have to look 147. What is what these values mean in a table, which is right up here, where you have extreme values, right? So the extreme values, 147 means there's 5,000. There's somebody with who is 5,000 grams. There's a child who was born at with a weight of who had a weight of 5,000 grams or 5 kg, which in this case is an outlier. So like we said in the beginning, since we have very few of them, they're just about three, you can either replace this with a mean. So you look at those values and you go to your data set and replace with the mean to remove the outliers. Since there are not too many, you can do that. Another way is just to compare the mean with the 5% trim mean. So our mean is 3,323 and the 5% trim mean is 3,310. So the difference is just about 20 grams, which is not that big. If it was about 100 grams, then it will mean that these outliers can actually affect your result. But since the difference between the 5% trimmed mean and the mean are not that, the gap is not that wide, it means that you can allow it. You cannot even, you mustn't even go replacing them with the mean. You can just allow those ones there. All right. So this is just a recap of what we saw last week. And Our Shapiro-Wilk test, as we saw, it is significant, which means that the data is not normally distributed. Yes. So in this case, you interpret it opposite, which means our null hypothesis is saying that the data is what normally distributed. And so if our null hypothesis is not to be taken in this case because it is significant, it means our data is not normally distributed. But our histogram is fairly normal. It's fairly bell-shaped. So we chose to go on with our tests. All right, so that was it. And then we're trying to answer the question, the difference between the birth weight of the babies that were born through CS and the babies that were born vaginally or normally. So, and we say that now, so we have two groups. That's the first thing you identify. We have two groups. One group is those that were born normally, and two groups, those that were born using through cesarean section. So those are the two groups, and now you want to compare their birth weight. And since the birth weight is a continuous variable, the first test that should come to your mind should be t-test, because you have two groups, and you want to compare if there is a difference between the mean. All right, so to run your t-test, if you have any question, you can stop at any point and ask there, so that should not be more of a monologue. Did you understand the concept of
Yeah,
normality?
yeah.
Okay. All right. So now to do for our t-test, we are comparing means actually. So when you go to analyze, you will take compare means. Compare means. This is it. And then you will take what? The independent sample t-test. We are taking the independent sample t-test in this case, not the one sample t-test. The one sample t-test is when you have a mean that is gotten from another research, maybe from the general public, maybe somewhere. For example, maybe research has shown that the average birth weight is 3 kg. And so you went out and you collected your data. You just look at maybe you study files of children that were put to bed in a particular hospital. You took their birth weight, just those ones, just one variable. And then you want to see if it is true that the average birth weight is 3 kg. That's when you use the one sample t-test. In that case, when you click it, they will ask you to put the variable. You put the variable, and then they will ask you to put the test value, this test value
Please,
here.
I didn't get that clearly. The one sample test, yeah, trying to explain it.
Is used when you want to compare your data with a known average value. Maybe from maybe that value is from research or from literature, or it's a test that you want to do. Maybe a laboratory test has shown that the average reading for this particular reagent is supposed to be this value. And then you collect values maybe over a period of time. And you want to find out if the average value indeed is what the manufacturer told you or what the teacher told you. So you put them all in one variable, like in this case, maybe birth weight. Then you come and choose one sample t-test. And then you send the variable to the test variable side. For example, if it was birth weight, and then where they say test value, you put that in that you got from literature. Understand? Maybe it was 3,000 grams, for example. Other options, nothing. Yeah, then you take, okay, that's one sample t-test. It's just one sample from the name. It's one sample. It's just one variable. And you have your result, as you can see. So when you look at it, you will see that this T here is what we call the test statistic. Every test that you use in statistics has what we call a test statistic value. The one for T is abbreviated T. The one for chi-square is abbreviated X square. Maybe I've seen it somewhere. Yeah, maybe I've also seen Z somewhere. Those are called test statistics. It's a whole statistical uh, maneuver things that are done at the back end. And then you have your p-value here, which is significant. And you have the mean difference. and we have the lower and the upper limit. So it means that your mean here is 3,323, as you can see, which is not very, very far from 3,000. So if this was a one sample t-test, we will be accepting what? Our hypothesis that indeed the average birth weight is 3 kg. You understand? Because we have compared it to a known mean, which is 3 kg. And we have seen that it's significant, as you can see here. P is less than 0.05 because we are using the 5%, 0.5% alpha, right? We're at 95% confidence. So any value that is less than 0.05 is considered statistically significant. And then this upper and this lower limit. For if you have not understood what this thing means, this lower and upper limit means that this the possible values that you can have if you conduct this experiment over and over again, you will have possible values that lie between what? This lower and upper limit. That's what these values will always mean for those if you have never really understood it. So these are possible plausible values. If you repeat this experiment over and over, you will have values that range between 263 to 384 for the mean difference. Okay. In this case, our mean difference is 323, right? So you always have a mean difference between
Mm.
value and this value. That's what these values mean. All right, let's do our independent sample test. I just had to show you this because you may need it one day. So let's go back and do our independent sample. And I will call this one independent sample because the two groups we are testing are independent. They are not related. It's either the baby was born normally or the baby was born through CS. So they are independent. You cannot have a baby who was born normally and then was born. These things that they always talk about independent observation. It comes from your research methodology. It doesn't come from your data. It comes from your research design. When you're designing your research, you ensure that it's not pick data for one person and register it twice. Like some people may want to do falsification. They will go to this person and take data and maybe put it under CS and then take the same person and put under normal vaginal delivery. That will make a data bias. And in that case, you have not respected what independence of observation. So it's more of a research design. So you come to analyze, compare means, and then you take what independent. Analyze, compare means independent sample t-test. In this case now, the test variable here is your continuous variable, which is birth weight, is what we're looking for. So you take birth weight, send it to the test variable. Then the grouping variable here must be categorical because there are two groups, group 1 and group 2. So did we categorize it? Let me check my data. Yes, this is it. This is number 22. Mode of delivery, you see now, it is coded as 1 and 2. Vaginal delivery is 1 and cesarean delivery is 2. That's what they're asking here under this grouping variable. So I'll look for that mode of delivery and I will send it to the grouping variable. Where is it? Is it mode of delivery? I'll send it here. Then when you send it here, you see some 2 question marks in brackets. In this case, they're asking you to define your groups. How did you code those groups? You click on it and they say group 1. How did you code group 1? You gave the code 1. How did you code group 2? You gave the code 2.
Please,
Yes.
in case where you check for the normality and you discover that it was not normally distributed, where you had to do the log, you had to transform the data by doing the log form of it. When it comes now to this independent sample t-test, will you still have to do but the normal uh, this one, or you will have to take by the log form that you did earlier?
You will take by the log form. But now when you're reporting your data, you're going to convert it back to the normal unit. Because if you take the log
You
form,
have
you will no longer have that 3,000 grams. It will be reduced, right? Maybe it will be 3 point something or 0 point something.
mm,
Yes, but when you're reporting your result in your Word document, you will not say that 0.3 gram. That will not make sense. It will no longer be a unit. So you need to convert that maybe the mean that you have, you need to convert it back to what? To grams by taking lean. You know lean, right? It's a lot of but that's just in the case of reporting. The other ones still remain the same.
okay, the method of the analyzing remains the same.
Yes, but you use now but the transform variable. But when you transform, you have a new variable.
Mm.
Yeah. All right. So in defined groups, if you coded it as 0 and 1, you put 0 and 1 under defined groups. That's just how it is. Then I think options, we don't need anything. It's already 95% as you can see. For the confidence interval, I think that's okay. Then you take okay. Then let us see the output. So our t-test begins with group statistics. So it first of all tell us how many participants were under, or how many babies were born under normal vaginal delivery. We have N, 136. We have the mean and the standard deviation and the standard error. And then we have cesarean delivery. There were 100. We have the mean, standard deviation, and standard error. Standard error of the mean. Let me see. Do you understand what standard error of the mean is?
No, not really.
Okay. Anywhere you see standard error, they're just telling you the degree by which this your mean now, it differs from the actual population mean. And when we talk about actual population mean, we're talking about an expected value. Since we're working with a sample, we're not working with the entire population on Earth. We're working with a sample. Using statistical methods, the software can be able to estimate what the actual population mean could be. You understand? So, and we don't expect that your standard error should be too large. That's just the logic. If your standard error is too large, maybe 1,000 or something, it will mean that your data does not really represent true population. And that's why sometimes students who do fraud can be caught. Because it is true that if you collect real world data, there should be some patterns, some resemblance. But now those who do fake data, sometimes you may have too large standard errors. And it may not, in that case, you will not consider your data. As you do data analysis, you will realize that most often in some tests, when you run t-tests sometimes, you will see that some particular ones have uh, very large standard errors. And when they have those large standard errors, you will notice that their p-value is not written, or their 95% confidence interval is empty. When it's empty like that, it means that the software does not really, in fact, it means that your data does not represent the true population, and so you cannot have an estimated confidence interval. That's just it. All right, so let us see the next one. Just give me 1 minute. just want to check my literature about this. Okay. All right. So now, independent sample t-test, we move to our table of to interpret our table for the t-test. We have equal variances assumed and equal variances not assumed. So we are going to look at the first one. So for t-test, we have this F here, the Levene's test for equality of variances. So you see that we have the Levene's test here for equality of variances, and it is not significant for equal variances assumed. So when I say equal variance, assume that in the two groups, they assume that they have approximately the same variance. Then in the second one, they don't assume. Hello.
Please, can you explain that again? This equal variance
I'm,
assumed.
I'm saying that equal variances assume means that you are treating the two groups that we are here, that we have here is the group that were born normally and the group that those who were born through CS, right? So they are assuming that they have the same or almost the same variance. You know what variance is, right? The degree in which the data spread across the mean from the middle
Yeah.
point, from the middle value, from the mean, the degree at which the data spread. So they're assuming that the data spread almost the same kind of way for the two groups.
Okay.
Yeah, so you're choosing as they have roughly the same level of variability. Then equal variance is not assumed is just the opposite. All right. But there's one that we have to choose. Let me, it's been a while I've not done t-test. So, all right. So I'm going to check our Levene's test. If our Levene's test is greater than 0.05, we're going to interpret the equal variances assumed. But if our Levene's test is less than 0.05, we'll interpret the second column. Equal variances not assumed. So it's that easy. So what's our Levene's test here? Which value can you see for the p-value? This is our Levene's
It's
test here.
is the 0.761.
Okay. Is it greater than or less than 0.05?
It is greater than.
It's greater than 0.05. So we're going to choose the first column. So we'll focus on this first column. It means equal variances have been assumed. I think you get the logic for this Levene's test, right? The Levene's test is almost like that Shapiro-Wilk test, which the new hypothesis states that equal variances have been assumed. That's why if it is not significant, you will actually take it. If it was significant, it means that equal variances are not assumed. And we'll take the second one. I don't know if you understand the logic.
Yes.
So always know that in every the statistical test, your p-value, your hypothesis is what actually guides you. And every test has a hypothesis. Just like we're running this test like this, we should have our hypothesis. maybe to say that there's no difference, right? That there's no difference between the birth weight of those who were born normally and those who were born through CS. That's our hypothesis. So we're going to see if if we will be proved right or wrong. So the Levene's test is like somebody, right? Is a statistician, a mathematician who, you know, wanted to talk about these equal variances, assume and not assume. So he came up with a mathematical formula which has been embedded inside this software to bring us this result. And he's also had his own hypothesis. And his null hypothesis was that equal variances should be assumed. You understand? And if equal variances should be assumed in every hypothesis, the positive one should always be greater than 0.05. That is why your alternative hypothesis in your research is the one that you are going to find. Because in this case, if we were going to find out to prove that, or if in our mind, right, in our mind we wanted to show to show out that there is actually a difference between the birth rate of babies born through CS and normally. Our null hypothesis will be the opposite, right? I'm sure you know this already. Our null hypothesis will be that there's no difference. You understand? So that if we go now and we see a significant p-value, we will then say that there's a difference. So that's the opposite with these other guys. They're on their instead opposite. Their own node is instead that there is what equal variances. That is why if your p here was significant, you will say that there is not equal variances, and you will take the second one. But since our p here is not significant, it means it matches what this guy is saying, this living guy is saying. It means it matches what he's saying, that there is actually what equal variances. And so we're going to flow with this first rule. That's how you interpret your t-test. Because you cannot carry these two and put on your result. You need to choose one. Even if you copy this table and paste, you should interpret based on what your living test tells you. All right. So we have our test statistic here, which is negative. And then we have our degrees of freedom. This degree of freedom is the sample size minus 1, right? Which means our sample size was 235. Was 236. Maybe there was one missing value. Then we have our significance here, 2/8. So you can see very well that it is not significant, right? It's 0.862, which means that there is no difference between the birth weight of those who were born through vaginal delivery and what CS, which means we're not going to reject our null hypothesis. And this is the main difference between the two groups. And then we have our standard error. You see that it's not that large, right? It's not even up to 100. And then we have the lower and the upper limit. And one thing too for this lower and upper limit is that if the range contains 0, it means that it's not significant. How will you know that it contains 0? You start from the lower limit. If you start from this lower limit and you want to reach this upper limit, will you pass through 0? That's what you ask yourself. This is negative 133. If you want to pass and count, if you have to draw a number line, right? Remember number line from 0 from 2. You have to draw a number line and leave this negative
Yeah,
163,
you.
111. You will pass through 0, right?
Mhm.
Yes. It means that your data is not significant. If it was significant, you should not have 0. Either it's negative 103 to negative something, or it's positive to positive, you should not have 0. So this further confirms this p-value that is not significant like this. So we can conclude here saying that there is no difference between the birth weight of babies born through CS and those born vaginally. There's no difference in our study. Although some literature will tell you that babies who are born through CS is because they have so much weight now that they cannot pass through the vagina. But that's just one thing. That might not be the case. In some cases, it can be that the woman has an issue or has been operated many times. That's why they have to stay pass. So there are many reasons why you can use to explain this your result. If you do your discussion, you can use other articles. Maybe it's not taking into consideration the number of times the woman has given birth through CS and all those things, what they were eating during pregnancy, and if they, all those other items, all those other factors, they may have contributed to causing a change in those people's research who say that there is a difference. But in our own research, there's no difference. So that's how you interpret your t-test. You run interpret your t-test. I don't know. Is there any question? Do you understand it?
Mm. So if I can understand, the main things that you use to interpret the t-test is the p-value, the standard error, and the lower upper limit.
Yeah, but you start with your Leaving test to know which role to choose because you always have these two roles: equal variances, assume and not assume. Once you look at your Leaving test, the p-value for Leaving test will tell you which role to choose. Once it is significant, you choose the second row. If it is not significant, you choose the first row. Then you just continue now. You focus on your p-value. That's
So
the
if
first
it
thing.
is significant when you are choosing the second row,
You interpret
how
that the
do you
second
interpret?
row.
How do you
The second row has p-value too now. This is its own p-value, 0.863. Although they're almost the same, but at least there are some slight differences. Its own lower limit is 134, negative 134 to 113. You see,
and
right?
that's its own standard.
Yes, this is not standard error. And this is one mean difference.
And the degree of freedom is 206.
Mm-hmm. I don't know how they manipulate to have this. Because normally degree of freedom is 10
And the
minus 1, right?
degree of freedom there is still calculated as f minus 1.
That's what I know. So this one up here is the right one. This one sample, no, that's one sample, right? See our degree of freedom here is 235. You see, right? It's 236 minus 1.
Yeah.
Yeah, but for this t-test, I don't know what they do. The DF is different. Maybe I'll read about that. Maybe I can just check. Okay, yeah, there's a different formulas to do their own. Things you are saying.
Mm,
So I was not even record that. Yeah, so the way to calculate the degrees of freedom for t-test is different because you're dealing with two groups. And that's it in the chat box. The formula is there. And you can read more. Any question?
no.
All right. If there's no question, then we are going to move right away. You can do chi-square test, right?
Mm, no, no.
Haven't you watched
But
demo
I
one?
watched the video, it's just that I really did not understand it.
But he's not asking me a question now, Madam Ann.
I've really been since the lesson began, to be sincere, I've not really been able to really follow it because I've even been having on and off. Even last lesson, I was able to follow with my laptop. 2 days ago, the laptop still gave up. So I've not really keenly followed the lesson from the beginning. I've just been watching the video, but to really practice like that, it has really been a challenge to me.
And that practice is even the most important thing. Because when you watch the video, you will
Mm,
see it's very easy. When you want to practice it before you realize that it's not that easy.
yes.
But it's a course, as I'm watching the videos and even the recorded versions, does it meet your expectations?
To be honest, most of these things I really in my own let me say what I do, like what I really needed it for, I've not really been able to touch it, because most of these things are when we do data analysis in the sciences, not social sciences, we hardly deal with questionnaires, because most of your videos and the lessons are based on maybe analyzing questionnaires and stuff like that. But most of us, we deal with direct analysis that you get from the lab. Like maybe you are measuring, maybe you are doing a analysis that you have to deal with chemicals and record the amount of chemical used and things like that that you have to analyze. But to I've not really gotten that, because that was one of the reasons why I had to look for this SPSS to understand it.
The concept is the same. When you analyze or you're doing the thing in the lab, what is your objective? What do you want to find out?
It's most to compare means using ANOVA test.
That's it. I've done one today now. I've done C tests. You compare the means of this test with this test. If you have two different reagents and you're testing for something in those two different reagents, when you conduct, let's say, one, two, three, four experiments using this reagent, you record your samples, right? You record it. Then you compare, you test for the other reagents. You record your samples. In that case, you can do ANOVA. And there's a way to arrange your data in that particular case, because if you're doing t-test, they'll still ask you for what group one and group two. In that case, you arrange your data differently. Let me show you how to do that. If you have two of them, because we're rounding over this thing and you should be able to get one thing. All right, you can see my screen, right? The variable view.
No, maybe you should share it
You
again.
are still seeing the result view. All right.
Yeah,
Variable view, right?
yeah, I
Now,
can now see it.
let us assume that you are carrying out two experiments. You group them, all right? Experiments in group one,
Mm,
experiments in group two. You name one of the variables groups. The second one, you'll be experiment. This is how you do that one. Experiment. You come to data view. You have groups, right? You have experiment. Your groups, they're just two groups. And maybe you have done maybe five different tests with group one. So I'll write one, 5 times. Then you have done maybe five tests two for group two. I'll do it 5 times. That's how you do this one. Of course, this one is categorical. So I'll come to these groups and I'll change it to this category or nominal. This one is scale. Right. Now, experiment one in group one, what was your result? Maybe it was 200, I don't know, for example. Experiment two in group one. That's in group one, that's in reagent one. Let's call this one reagent one. Maybe it was 242. Maybe you had 182. Maybe you had 450. Maybe you had three diseases. You understand now? Now
yeah.
you're now in reagent two. In reagent two, what did you have? You put them. You put all those values you had. If they're just two reagents that you want to compare, that is t-test you're going to use. If you are doing three reagents, you come and put three here, and then you continue. In this case, I'm going to use ANOVA. Well, I'm not yet done ANOVA. Because ANOVA, you have more than one group. But in this case, you have just two groups. So you have these two groups, and your idea will be that you want to find out if there is a difference with these reagents, these two reagents. Which one is better than
Mm,
the other, right? First of all, you're
yeah.
going to look for their means. Maybe you are comparing it to maybe a standard. Maybe there's a standard somewhere, and you want to see if the mean of reagent one is close to your standard, or the mean of reagent two is close to your standard, or if there's even a difference between the means of these two reagents, right? You do
Yeah.
your t-test. When you do your t-test, you look for the mean for group one and the mean for group two. Or you can first of all do your t-test, look for the mean for group one and the mean for group two. If you do it here, it might even be disturbing because we have used a different data set. We have this thing missing values here. But let's just try it. Independent sample. Okay, let's first of all rename it. So value one is reagent one. Value two is reagent two. All right. The test. Let's reset this one. That's the experiment is those values you got. Then your groups here are those groups. And how did you label those groups? You have group one and you have group two, or reagent one and reagent two. And you continue. You have the same result a similar result that we had for the other one. You see the mean for reagent one and mean for reagent two, right?
Mm-hmm.
You see that they have two different the means are different. Those the results are different. Meaning that the two reagents give you two different results. But now the question
Yeah.
is that is this statistically significant? Can you confidently say that one maybe you are trying to find out which reagent is better? Maybe you are comparing it to a particular standard, or maybe an outcome. In this case, we don't have outcome. If it was patient, we talk about outcome. If the patients fare better, if the patients you can score if the patient scored 8 on 10 feeling better or what. But in this case, it's lab reagent. So maybe you'll be comparing it to a standard, or maybe you want to find out if it's actually a difference between the reagents, the result produced by these reagents. And now you have done it, you have seen that for real, the means are different. There's a difference actually. But now this difference you are seeing, is it statistically significant? Is it true? Can you apply it in the real world? Can you really confidently say that the two reagents are different? They have different maybe efficacy. I don't know how they call it, people call it in the lab. I left the lab a few years ago. How do you do that? You come to your Levin's test and check, first of all, your Levin's test here, significance here shows that what it is significant. You can see now.
Mm-hmm. It's
So,
less than 0.1.
voila. So you're going to choose by the second row. So you're going to interpret, but the equivariance is not assumed. And then you come straight and look at your P now. P is 0.28. It means that although there's a difference in the means of these two reagents, it is not statistically significant. So this difference could just be due to chance. It means that the two reagents are not very, very different because their mean here is not significant. You
Mm-hmm.
understand? And of course, the other ones is the position is the same. But in order for you to be confidently use statistics to tell this, you must have at least 30 values. I don't know if people, yeah, that's what people do. The minimum sample size for you to have this kind of confidence in your statistical result is at least 30, if a sample size of 30. If you have less, it may not really be true. That's what I can say from my own experiment. But at least from here, you can see that although there's a difference in your test result, it is not significant. So how do you conclude?
Mm-hmm.
You can conclude now by saying that the two reagents are almost the same. You understand now?
Yeah.
Now, if it was significant here, if this P was significant, you will say that the two reagents they are not the same. Means that one may be stronger. And now to know which one is
Yeah,
stronger,
Daniel.
you can now look at it and compare now with the real with maybe a standard. Which of these mean is close to your standard, or what the literature says. If it's reagent one,
Mm-hmm.
then you can take reagent one. But now that they are not even significant, it means the two reagents. They are not different. Means they're almost the same. They can now choose the cheaper one. Maybe you wanted to find out which reagent to buy. You can buy the cheaper one since of course you have seen that the two of them have almost the same strength. The difference is not significant. All right. So I think that you can try this one, right? You can try this one with one of your. That's why I've been asking for your data.
Mhm.
Now, what data are you using? Share it, let us analyze so that you can feel the SPSS. So you most of the time you'll be using both t-test and ANOVA for your research because you are basically focused on laboratory experiments. You'll be using t-test, but at least still know the other ones because someone can still bring the data for you to analyze and still make some money. Because normally to analyze data for a master's student, at least is 50,000 at least. And then if the data is too complex, you can be charging as high as 70,000, 75,000. Not to talk of PhD. People will be paying like 100,000, 150. All right, so that is it. And you try it, and if you have your data, if you have some experiments you have run, right, and then what was the objective? Share, just if it's in an Excel sheet, just share it so that in the next class we should analyze it. At least you have been following the course along. You should not,
Mhm.
yes.
Yeah.
All right, so let's just look at the data set again and see if we can do t-test for one of them so that where is it? Is this it? Yes. All right, not t-test, chi-square. Chi-square is a non-parametric test. So you should always use it when you have categorical variables. So it means that in this your case, in your research field, you may never have categorical variables, except you are grouping into reagent one, reagent two, reagent three. That's the only way you will categorize. But in other ways, you will not be working with this our chi-square thing. Yeah, and you may also need to do regression sometime, because you may want to do two things to see maybe increase in this outcome. Does it lead to increase in this? Does this reagent cause an increase in maybe heart rate or an increase in wavelength? Or I don't know. I'm not. If I was in your field, I could give many examples. Sometimes that's when you use regression. Regression is simply asking yourself if increase in this thing will lead to increase in the other one, or if decrease in this will lead to
Mm-hmm.
decrease in the other one. That's just the meaning of regression. And so you may need to use it someday. So in your research work, you may be working with t-test, ANOVA, and then what? Regression. All right. So let's look at our data here. And okay, they have group this gap days now. Which one are they doing group day? Let me look at some categorical variables here. Let's just run chi-square test so that you understand it. Because many times you will do chi-square test if you're analyzing data for students. You will do chi-square test. It's one of the most common. It's not even put the oh, la, la. It was only this okay. So we have alcohol consumption and mode of delivery. As you can see here, number 16 is alcohol. What am I doing? Okay, number 16 is alcohol consumption, 0 is no, and 1 is yes. So this it may just be a stupid objective, but let's just use it to practice chi-square test to find out if consuming alcohol during pregnancy can determine the mode by which the baby is born, maybe through normal delivery or CS. Yes. So in this case, you have to know that the two variables are categorical. That's it. And since they're categorical, there is no need testing for normality and all those things. You just go ahead and run your chi-square test. And then what was the objective here? Is there an association? When you start hearing the word association, you know that we want to see if there is an association between consuming alcohol during pregnancy and giving birth through CS or what normal vaginal delivery. Is there any link? So just know the concept when it is used. When you know the concept, it will not be a big deal. Know the concept and know how to interpret. So it's analyze descriptive statistics and then cross tabs. In this case, I'm going to do cross tabulation. So you can choose anyone to send to the rows and the columns. But I would like to send I always try to visualize how I will prepare my result in Microsoft Word. So I would like to put delivery, alcohol, yes or no as the columns. So I'll take this one and put it as columns. And then I will take mode of delivery and put it as my rows. And then I'll come to statistics and I'll choose chi-square. If you don't choose chi-square here, you will not have it. If you wanted to do correlations, you can choose correlation. And the difference is that correlation will give you, the correlation coefficient will be a value between 0 and 1. That's just it. And the closer the value it is to 1, it means there is a strong correlation. The further the value is away from 1, it means it's a weak correlation. So if you have something like 0.1, it means it's a weak correlation. If you have something like 0.8, it's a strong correlation. That's just the difference between correlation and chi-square. Chi-square will give you something else. It will give you p-value. It will give you chi-square test statistic. But correlation will give you just a correlation coefficient and maybe a p-value too. All right, so we take chi-square and under says, so we want to have percentages too, and we want to have it for the columns. Since we have chosen the way we want to present it, you choose column. You can still choose row and total, but you give you a lot of data. I will just choose column here and then continue and take OK. And then we look at our results. It will give us two tables. The first table is a cross tabulation. You see that my alcohol is on the columns as I put it, yes and no. And the vaginal delivery and the cesarean section are on the rows. And how do you interpret it? You interpret it column by column. So for those who do not drink alcohol, how many percentage or how many of them were born, they gave birth through vaginal delivery? 121, that's 56%, right? So those who don't drink alcohol, more of them give birth normally than those who drink, than those who drink alcohol. Anyway, we are focused on those who don't drink alcohol. More of them give birth normally. Then for those who drink alcohol, as you can see, yes here, more still give birth normally because there are just 20 of them who drink alcohol, as you can see here. Out of those 20, 15 gave birth normally and 5 gave birth through CS. So you see that in all, those who gave birth normally are still more, whether they take alcohol or not. But we look at our p-value. This chi-square table, as you can see here, this first value here is the p-value. You see now, Pearson chi-square value is 2.7. This way you always see the right X square in research articles. And then the p-value is this asymptotic, you can see exact SYG. That's significance. It is not, it doesn't appear under Pearson chi-square. Sometimes it will not appear here, but it appear under Fisher's exact. Why does it appear under Fisher's exact in this case? It's because this table up here is what we call a 2 by 2 table. If you ever heard about 2 by 2, 2 by 2 means that we have two
Two
rows.
by two.
Yes, means we have two rows and two columns.
Mm.
Once we have two rows and two columns, chi-square test will not be computed. What you have will call Fisher's exact. But if we have something like three categories here, maybe vaginal delivery, cesarean delivery, or maybe miscarriage, if you have something like three categories here, or more than two in any of these, then you have chi-square. You have chi-square p-value here. Because some teachers will just tell you that, oh, go and do Fisher's exact. Go and do Fisher's exact. They don't know that the test it depends on how your data is. All right, it's already 9. I think we are just going to end here. It's better we push on over to next week. if you have your data, you share so that we can do your ANOVA next week so that you understand better. Because next week we'll do the ANOVA and we'll do regression. And that will be all for the live sessions. We'll only organize if you have maybe a data to analyze and you want me to help out, then you can reach out and then work it out. All right. Any
So
question?
for this chi-square test, what
Mhm.
we look at is just this Pearson chi-square value and this Fisher exact
And the
to
p-value.
discuss.
You look at the Pearson chi-square value and your p-value. But in the case where you have a 2 by 2 table, like in this our case here, you will just focus on Fisher's exact. But Fisher's exact does not have
Mm,
the value. You see that in under Fisher's exact, you don't have anything under value, right?
mm,
So you will pick by this 2.7, the Pearson chi-square value. Then for the p-value, you come and pick this 0.15 because there's nothing under
mm,
Pearson chi-square. But in other cases where it's not a 2 by 2 table, you are going to have your
yeah,
Pearson chi-square value here, and you're going to have your p-value here. Which one am I
mm,
even talking about? No, we're looking at this other one. Oh. Sorry. The p-value we are focusing on is this asymptotic significance, two-sided. Always take note, this asymptotic, please, not this exact. So the p-value is there,
we
but
have point one.
here is zero point 0.1. But in this particular case, since we have 2 by 2, you choose by Fisher's exact. It's 0.15. It's almost the same thing. But you never choose one-sided. But we're working with two-sided now. Remember that our histogram, we are focused, we look at the both sides. In some cases, in some research models, they'll look at one-sided where they focus only maybe on positive, or they focus only on the right extreme or the left extreme. Depends on some of those models. But in our case, for now, we're looking at the two-sided. So if you are looking for Fisher's exact, you will choose this two-sided. Otherwise, you're looking at asymptotic significance here, still two-sided. You get the point now.
Okay.
Mm.
Mhm.
I will share a video on how to interpret your chi-square. There's a video on it, how to do it, because you need to report these counts here and the percentages. All right, any other question?
No.
All right, so I'll share this for those who have been able to join so they can catch up. Then next week we'll see how to do ANOVA and regression. Meanwhile, if you don't mind, you can share your data. But some of those, no, I know some data sets are confidential, but if you can share.
No, I'll share.
All right. Yeah, when you share,
I'll share.
you share the objectives so that we can start with that next week. We can share within the week.
Okay.
Yeah. Okay.